Just a minute. Just I will introduce. Okay, I'm starting. Then I will introduce Juliana first. So,
Okay,
hi
thank
everyone.
you.
Yeah. Hi everyone. I'm Sachin Mishra, the co-chair of ICAC ECR committee, SSC committee, and I welcome you all for this seminar, online seminar by two eminent speakers in this field who had recently got the doctors in atmospheric sciences. And yeah, we have this online seminar sessions. If you like to showcase your research or have want to network among the researchers in your field, then it's a good platform to present and interact with the ECRs globally. So you can feel free to write to us, and we can keep a slot ready for you in the upcoming years so that you can interact with us. And with this, I would like to invite Juliana, she's the SSC member, and to host the meeting and introduce the speakers. Thank you.
Thank you, Sachin. Hi, everyone. Good morning, good afternoon, good night for everyone in the different times. Um, it's my pleasure to introduce you today to the IGAC ECR seminar. My name is Juliana Mejia, and I will be moderating today's session. And today we have two invited speakers, and each speaker will have around 15 to 20 minutes for their presentation and will be followed by a 5-minute question time. So keep in mind that time. And if you have any questions, please feel free to write them in the chat or keep them to the end of each presentation so you can ask the question during that part during the 5-minute question and answer. And our first speaker is Dr. Ishir Dutta from the Massachusetts Institute of Technology, MIT, from the USA. Dr. Dutta recently earned his PhD at MIT, where he studied long-term trends, precursors related to PM2.5, ozone, and acid rain, with a focus on nitrogen oxides. Before that, he worked at a tech startup in the Bay Area and completed his undergraduate studies in physics and mathematics at Colgate University. Today, he will present a talk titled The Global Tropospheric Budget of NOI. And please join me in welcoming Dr. Dura. Please, Dr. Dura, the floor is yours.
Thanks, Juliana. That's a very nice introduction. Thanks to the conveners for organizing this and for the invitation to speak. Thanks for all of you for making time at various times of your day to listen. I hope everyone can see my slides. All good? Amazing. As Juliana said, my name's Ishir, and I somewhat recently wrapped up my PhD at MIT, working with Professor Colette Heald. I'm really excited to talk to you today about some of our recent work that has to do with oxidized reactive nitrogen, funded thanks to the United States National Science Foundation. So I don't think I need to give too much of an introduction since this is an atmospheric chemistry crowd. So I'll start here. I pulled this figure from Kroll et al., which I think does a really nice job of summarizing some key features of tropospheric chemistry. Reactive nitrogen, if you can see my cursor, yes, hopefully.
Yes.
Reactive nitrogen is on the top part of this figure. Nitrogen oxides are on the top left. As you can see, their cycling drives the formation of secondary pollutants like ozone. And then obviously, like further down this complex cascade of chemistry, you form PM2.5, but also intermediate air pollutants and environmental pollutants like nitric acid, which is a component of acid rain. The top right is the reduced nitrogen side of the story, which we won't address today, but might be the subject of future work. It's important to study this chemistry because we've kind of increased the importance of this chemistry over the last century and a half since the pre-industrial. And on the left, you can see the change in ammonia emissions over time, somewhat broken down by countries and major sources. But the key figure in both of these graphs is that there's no single country that's contributing to the bulk state of this problem. It is very much a diffuse global problem. And so it becomes ever more important to characterize sources, to characterize sinks, and of course the intervening chemistry. The first such study that I could find that assembled a budget was work done by Jennifer Logan, working at Harvard in 1983. The left side, I've pulled a table from her paper, which is a fabulous read. It's really quite remarkable, that shows sources. So you see what we think of as common NOx sources, fossil fuels being the largest, but then also natural sources, including biomass burning, lightning, soil activity. And on the right, I've shown some major sinks. This is primarily in North America estimates. And a key feature of this table I would draw your attention to is that there are four key species, right? There's the NOx species, so NO and NO2, and then the two sort of classical reservoirs, and then a sink of NOx in HNO3 and PAN. Some 40 years later, this is a more contemporaneous example that I've pulled from Murray et al. From a couple of years ago. And now, in the intervening 40 years, we've learned a lot about nitrogen chemistry. We have a litany of different models. The y-axis is different models, and then the x-axis shows the estimated burden of NOI, broken down by, again, these same four key species. And I draw your attention to two aspects of this figure. One is that there's a fair amount of disagreement between these models, and two, they seem to focus primarily, even 40 years later, on the same four NOI species. And so in our work, we wanted to take a more comprehensive approach to characterizing this budget, incorporate some of the learnings of the last, almost half century, and include the veritable zoo of nitrogen species that we now know about and study, but also include some of the key chemical transformations that happen in the atmosphere that are not captured by a simple snapshot of burdens and deposition and emissions. To do this, we're primarily a modeling group, and so we use two tools. We use the Geoschem chemical transport model, which many of you, I'm sure, are familiar with, so I won't spend too much time on that. We ran it pretty much straight out of the box. We didn't make any major modifications, but we did add tracers for every NOI reaction to track mass as it moves through the system from emission to transformation to deposition. The second tool we use is data from the ATOM flight campaign, which, again, many of you are certainly familiar with. And we do this for two reasons. One is to evaluate the performance of the model, so we get a good sense of what the remote atmosphere looks like further away from sources and whether Geoschem performs well at characterizing NOI chemistry. And then two, to sort of set a baseline and contextualize some of the results that we will present as a budget from the model. So to start with the observations, here I've shown stacked vertical profiles. The left-hand panel is directly from the ATOM measurements, and the right-hand panel is the model sampled at ATOM flight times. This is ATOM 1, Northern Hemisphere, so summertime, July, August of 2016. The x-axis in PPT, and this is total NOI broken down by each of the species that I talked about before, so NOx, PAN, and HNO3. I would argue that the model does a pretty decent job of capturing this vertical profile. Slight high bias, but the structure is pretty reasonable. The high bias, I would argue, is mostly attributable to a high bias in nitric acid, shown here in red. This is a pretty long-standing bias. It's existed since my advisor was in grad school, and has been the source of much discussion and debate within the Geoschem modeling community. And we haven't been able to quite nail down how to address this bias. And we hope that some of our work will provide a framework to tackle this problem in a systematic manner. But this is only one hemisphere, it's only one season. And so I can zoom out and show you this comparison across seasons, across hemispheres. So this is pairwise observation and model. The top row is all Northern Hemisphere, the bottom row is all Southern Hemisphere. So you have summer, winter, fall, and spring pairs. Again, the key species remain the same. And I would argue the saturated observation structure is roughly matching the desaturated model structure with a high model bias that, again, you can see quite clearly in most pairs is attributable to HNO3. In some areas, it's PAN, but the model performance is not terrible. So a quick overview of how we did assemble this budget as a burden, as a steady state of a combination of NOI species. So given an example NOI species, the burden is set by a steady state of the fluxes, so starting from emission, the chemical processing within the troposphere, production and loss to various other NOI species, and then their eventual deposition. I've got a worked example. So pan, sort of what we think of as the canonical reservoir species, and an important component of photochemical smog. It's the stuff that makes your eyes sting. It's one of the things that makes your eyes sting in smog. Is produced, by this sort of pressure and temperature dependent reaction of the peroxyacetyl radical with NO2, which is sort of thermally unstable and then dissociates back into this peroxy radical and NO2, but the mass is not quite balanced, right? So there's some net loss to form smaller fragments of methyl peroxide radical, CO2, NO2, nitrate radical, and then a small fraction that dry deposits and a fraction that wet deposits. And so this is roughly what we'll be doing for every NOI species and then accumulating it into a full picture of the tropospheric budget. Warning, I'm just going to show that on the next slide. It is a fair bit to take in. Don't worry, we'll break it down. And if I don't talk about your favorite section of NOI chemistry today, feel free to email me or read the paper. It's up on ACPD. We can chat in more detail about something I missed today. But just to situate you, the big blue bubbles are again the burdens, like in the last example. The vertical red arrows, most notably this emissions of NOx as NO, is emissions. The downward facing vertical arrows are dry and wet deposition, respectively, in yellow and blue. And then these curved arrows represent chemistry with relevant reagents marked and the net fluxes at the arrowheads between species. So I would say the first feature, which is kind of a good thing to see, is that the four biggest buckets on this graph are NO, NO2, PANs, well, all peroxynitrates, of which PAN is the largest component, and HNO3. So now these are very much still the big buckets that we've been studying for the last half century. So that's somewhat reassuring that we're not barking up the wrong tree. The second feature is if you take a look at this sort of messy spaghetti of chemical fluxes, and I ask you to pick out, what is the biggest flux on this diagram, you might say, well, there's this pretty big radical flux between NO2 and NO3, but I would argue that's pretty fast cycling, so it doesn't represent really a removal of NOx from the system. We have to take a little bit of a closer look and look at this. NOx removal by photolytic oxidation by OH to form HNO3 is one of the largest fluxes in the global troposphere. This HNO3, gas phase HNO3, equilibrates, does acid-base chemistry to form particulate nitrate, aerosol nitrate, which is an important component of PM2.5. And together, this total nitrate system, as HNO3 plus nitrate, is responsible for almost all the removal of NOx as NOI from the system. And that removal is roughly split evenly between wet and dry deposition. Now, obviously, that varies quite heavily regionally, depending on precipitation and land cover types and so on and so forth. But globally, it's pretty evenly distributed. And that's why we think of nitric acid as sort of this terminal sink of NOx. Once you form nitric acid or nitrate, certainly one doesn't recycle NOx. It's most likely to get deposited and removed from the system. More recent work, about the last decade or so, has argued that there is a recycling pathway of nitrate photolysis or renoxification, which is the current area of study. It's a highly uncertain process. We don't quite know what the reaction rates are. We don't quite know how efficient this is, whether it depends on the surface qualities, whether it depends on the mixtures of the PM2.5. But we implemented the model as is, which sets the photolysis rate of this particulate nitrate at about 100 times faster than that of gas phase nitric acid. One may argue whether that's appropriate or not. I'm happy to do that offline, but we wanted to assess the model as it stands. And so this returned recycling flux back to HONO and then also directly to NO2, which effectively both recycles NOx, given that HONO cycling with NO is so fast, now represents a pretty substantial amount of the total flux flowing through this aerosol nitrate. If you look at the sum of these fluxes, it's about 12 teragrams of nitrogen per year, which is comparable to, on the order of 13 teragrams of nitrogen that are physically removed from the system that we think of as, or used to think of as a terminal sink. And so, it's sort of, it's complicated or complemented our understanding of the system, and it's perhaps more appropriate, regardless of how fast this chemistry is going, to think of nitrate as a sink, as a reservoir rather than a canonical sink. I'll return to the figure I showed from Murray et al. Now I'm showing the fractions as well. And you might be asking the question, well, how does geochem stack up in this intermodel comparison? As you can see, right, the smallest burdens, which I believe is the Oslo model, is something like 3 times or 4 times as a fourth as much as some of the largest burdens of NOI. This is one of the GIST models, I believe. And so how does this geochem simulation stack up to the competition? I've remade this figure to be a bit more legible for our purposes here. And this is all data from Murray et al. And so the top bar is the study. So again, like just for a one-to-one comparison, I've just put the 4 species that they put in their original paper. So NO, NO2, HNO3, and PAN. And there's a fair amount of disagreement, right? Like both in some relatively straightforward, what we think of relatively straightforward things as the NO to NO2 ratio, the NOx to NOR ratio, but also the abundances of HNO3. And as we saw earlier, GeoScam has a pretty high HNO3 bias, but then some models have almost twice as much HNO3 as GeoScam. So we really do have to do some digging to see whether we're representing this chemistry correctly. Now, as I argued earlier in the talk, this is not obviously the whole picture. There's a litany of other species that also are involved in this NOI cycling. And so adding those on, you get a pretty substantive addition to what would have otherwise seemed like a middle of the pack kind of budget. And we argue that, a more expanded view, obviously a lot of the aerosol chemistry is very simplified, perhaps gives us a better sense of how this nitrogen mass is moving through our troposphere now here. To wrap up, some key contributions from this work, which I hope you'll read, is we think the model does a fairly decent job of representing certainly remote area NOI chemistry over the remote oceans, notwithstanding this long-standing HNO3 bias. We've done, what we think is the first such comprehensive quantification of the flow of reactive nitrogen, in addition to a standard budget that shows burdens and deposition. And we've started to expand our representation of what a budget can look like, both in terms of the chemistry and in terms of the abundances of a greater variety of NOI species. I really appreciate the opportunity to speak, and I appreciate your attention. If any of you have questions about further details, the preprint is on ACPD. You can scan the QR code or look it up online. And if you have questions that I don't address or we don't get time to chat about today, please reach out by email. My website's on there. Most of my papers and some context should be on there as well. Thanks so much.
Thank you, Dr. Dutta. Very interesting presentation. So we're gonna start. If there is any question from the public, please feel free to write them. I can read them, or if you want to take the hand, we can give you permission to say the question. Okay, I do have
That was
one
extremely
question.
clear.
Yeah, it was a very nice talk, but I do have one question.
Amazing.
I'm not very much into the gas chemistry phase,
Uh,
so I'm just wondering what happens in the northern hemisphere summer from your vertical profiles that
mm,
your HNO3 and the PAN increases their concentrations while you go upper in the troposphere. It's very interesting to
mm,
see that trend. So I'm just wondering
mm.
why that happens.
Yeah, I think so. Pan is thermally unstable, right? So closer to the surface, temperatures are a little bit higher. So it generally dissociates back into NOx. And so unless you get a substantial amount of lofting to higher altitudes, lower temperatures, you don't. The Pan lifetime is quite short at low altitudes. So you'd expect to see far more Pan at high altitudes. HNO3 again, requires some amount of time to form. It's not super fast chemistry. Um, And so you need things to be at the right place at the right time. Like if you have a big biomass burning plume, then downwind you'll see some HNO3 formation, and that will be lower in the troposphere. But again, like it's sort of like a lofting and lifetimes kind of argument.
Okay, I see. So atom 2 would be winter time, like the
Wintertime northern
temperatures
hemisphere,
are
yes.
okay. Amazing. Yeah. Thank you. I think Sachin has a question.
Yeah. Hi, Ishir. It was a very wonderful presentation, and it was
Thank you.
quite informative. I was wondering, like, when you showed the diagram where there was a budget of nanovolt,
Mhm.
and
Yeah,
there I saw that the nitric acid. Here, the nitric acid, the dry deposition and the wet deposition, the quantity is comparable, almost comparable. And
yeah,
considering, like, if you look at the solubility of nitric acid in the atmosphere, it's quite high.
yeah.
So I was wondering, like, why it's not in terms of the matter, like the absolute amount, while the dry deposition and
Yeah.
wet deposition are comparable. So any thoughts on that?
Yeah, I think so. My last paper, which you could read, which is what this project was born out of, was looking at deposition measurements, both wet and dry. And I will say, one, I think um, if you find dry deposition, if you're forming nitric acid pretty close to the source or near the surface, it's very likely, especially like in urban areas, there's such high surface areas, right? Whether it's concrete or buildings, that you can just sort of deposit the gas pretty fast onto these surfaces. So you have pretty rapid removal near urban areas or sources of NOx. Katie Travis has some really wonderful work looking at some estimates of this over Korea. And she argues that, like our urban dry deposition models should be like almost 5x what we think they are, just because of the availability of surfaces on which this gas can deposit. Now, you're right. Like once you get some lofting, some interaction with moisture, you are much, much more likely to partition into the aerosol phase, at which point you will wet deposit. And then, so there's the spatial element of availability of moisture, of lofting, of the, land cover type, the emissions characteristics, temperature, and obviously you don't get any dry deposition over the ocean. So you have to strike a balance there as well. But it's quite uncertain, and I think dry deposition measurements are also all they're not direct measurements of dry deposition. Like most dry deposition measurement products that I've seen do sort of active sampling at, like 10 meters or 20 meters onto a filter, and then use a deposition velocity model to back out what the deposition would actually be. And so in a way, it's sort of inferred dry deposition. So one model might say a deposition velocity is X, and another might say it's 2X. So it's kind of hard to really nail that down.
Okay. Thank you. Thank you.
Okay. Well, is there any more questions? We can have maybe one from the public. If not, I think we can continue with the next speaker. Okay. Thank you again, Dr. Dutta.
Oh, thanks so much.
We are now continuing with our second speaker, Dr. Manuj Sharma from the Indian Institute of Technology, Tirupati, India. Dr. Sharma is an urban air quality researcher whose work focuses on air pollutant and greenhouse gas emission modeling, atmospheric simulative capacity, health risk assessment, and policy relevant research. Today, he will present Bridging Policies and Practice, Integrated Pathways for Cleaner Urban Air and Climate Co-Benefits from Road Transport. Please join me in welcoming Dr. Manuj Sharma. Dr. Sharma, the floor is yours. You can start your presentation.
Okay, thank you very much. And I hope my screen is visible. Please give a thumbs up. Yeah. So unlike Dr. Ishir, I am not an atmospheric scientist. My work is majorly focused on the cities and hyperlocal monitoring to understand how the cities in particular is behaving respective to the different sources and, air pollution and chemistry related to it. However, my presentation for this seminar or session is basically discuss that how the Indian cities are, experiencing with the policies and practices related to the existing and the future policies related for clean urban air and climate co-benefits coming out straight from the road transport emissions. So we are the three people which we have, me and one of my lab mate and my professor Suresh Jain from the Department of Civil and Environmental Engineering, IIT Tirupati. So I'll start with, first of all, introduction. We all know that especially in developing countries and developing cities, road transport is, plays a very a major huge role in urban air pollution. India, being as a fourth largest economy, as they said, is having the second largest road network, which is covering around 6.3 million kilometers. And based on one of the estimations, in 2030, we are expecting around 200 million vehicles, which are going to flying on that 6.3 million kilometer roads. Recent study published in the Lancet journal, you can check that around 0.87 million premature deaths has been caused by the outdoor air pollutions. And from that, 43,000 cases has been reported directly from the road transport emissions. Now, this road network might seem little complex, I would say, or informatics, but from the last 2 decades, the government or the national government has started implementing different kind of policies to make sure that the road transport emissions will be reduced. It started in 2000 when the country have got their first emission norms based on the European country. Like for example, in European states, you have a Euro 1, Euro 2. Based on that, we received as a Bharat Stage 1, what we called as BS1, BS2. And after 20 years now, the government and the regulatory agencies has more focused on how we can accelerate the electric mobility in our cities as well as in our nationwide transport vehicular fleet. But the problem with the policies which has been I have presented here is that most of them, or I would say all of them, are basically top-down approach. So you have some policies which have been proposed or implemented at the national level without any target specific measures for the city concentrate area. So what is happening? Like most of the policies are not able to implement properly on the cities. However, I would say that after 2022, that now the policies are being majorly focused on the city specific, with their or them, with the city's targets, so that the state and the city agencies can make their targets based on their compatibility and their accessibility, and they can implement it in the future. But most of the studies still now are focused on the mega cities, or I would say major cities like New Delhi, Bombay, Bangalore. And we still don't know about how the road transport emissions are behaving on the tier 2 non-attainment cities, because as the economy is progressing, tier 2 are also on the verge to become a mega cities in terms of vehicular fleet penetration. And the second important question is that how these road transport policies really, behaving on the road levels at these type of cities. Now, to understand the behavior on the impact, the very first question comes into the mind: how you will quantify the emissions? Because in air, you can have the monitors and you can, measure the concentration and do the source apportionment. But how we can estimate the knowledge at the source level? So what you can do is make a road transport or develop a road transport emissions using the IPCC tier 3 emission framework, and for vehicular specific, what we call an activity structure intensity modeling framework. The equation is more or less kind of linear relationship, but the two important factors which is required is the activity data, which is basically about the vehicular characteristics which are flying on the road. For example, distance traveled, fuel type, emission norms, how old is your vehicle is, what is the regular maintenance frequency for your vehicular, and the emission factors, which is basically a unit pollutant released from a per kilometer distance traveled from the vehicle. Now, this emission factor either you can develop, which require a hell lot of resources, or otherwise you can take it from the literatures. Like in Europe and in US, you have the COPET models and MOVE models. And India, what we use is the ARAI based emission factors. Now, for we are doing for different cities, but for this presentation, I'm showing for the Vijayawada cities, which is one of the southern Indian cities of the Andhra Pradesh state. Ishir is knowing around. I'm pretty sure that he's understand that where is the Andhra Pradesh state itself. But anyhow, and this is the road network where you'll see a complex, roads of the highways, RTLs, sub RTLs, which every type of roads you can guess it's passing from the city itself. In the coming slide, I'll show how the primary recording locations and secondary recording locations we have used. But a quick methodology framework that we have used, the first step is to understand the vehicular characteristics. Now, again, what we have followed is both the approaches, like we have been to the road and, performed some origin and destination survey where we have asked the questions like how old is your vehicle, what is the average distance travel that you use for the vehicle, what is the fuel efficiency, and some traffic flow recording that we have done at the different roads. And with the use of first and second component information and with some probability distribution, what you can get is the vehicle survival analysis, I mean vehicle survival rate, which will help you to understand, let's suppose if you will buy your vehicle today, then what is the probability that after 10 years, after 15 years, your vehicle will flying on the road or not. So this component is also, I'll just mark it there. So this component is also very important because you never know whether your vehicle is going to survive for 15 years or for 20 years based on what the government, the regulatory agencies will implement. So once you have the baseline emissions, the next step is to project the emissions for the future as well, because it is very important that you will able to quantify the impact of the policies which are going to be for the future. So what we have done, we have conducted a different type stakeholder workshops within state and the cities agencies to understand or to identify some indicators like GDP growth, vehicular number, vehicular projections, different type of vehicle technologies which are maybe in the future is going to penetrate in the city. And then we have come up with the scenarios called as a business as usual scenarios for 2025 and 2030. Similarly, for the alternative scenarios, again, we have gone through different policies and the programs which are which are proposed or going to be implemented for the futures by the national level, state level, and on the city level itself. So we have tried to integrate all the policies which are, implemented or in the regulatory agency's mind that is going to be implemented in the futures to develop some alternative scenarios for the similar years for 25 and 20, so that we can at the end have a city based on-road vehicular emissions and the energy demand as well. And that would be my fourth component. Again, so as I said that we have done some origin and destination based survey with my lab mates where we have asked the questions, and after that we have recorded at the different roads the fleet, and using the deep learning technology and Python based model, you can very easily identify what type of vehicle is flying on the road, the speed, and the average, the distance which is traveling for a particular stretch in a road. So it will help us to understand the actual fleet which is flying on the road comparison to the registration database, which the RTO in our case will tell you. So the survey result shows very interesting results. If I'll just say here that if you see the top pie chart, which shows you that from the last 20 years, around 71% of the vehicle has been registered as a two-wheelers like scooter, bikes, mopeds, and around 5% are three-wheelers like so on. However, when we have checked the vehicular survey results, 57% of the vehicles are registered as two-wheelers, where if you see that buses are of 12%, whereas at the time of registration, only 1% of the vehicles are registered as a buses. So it means lot of heavy or freight vehicles and buses are coming from outside of the cities as well. And on the left side of the table, if you see that overall, 51% of the vehicular fleet is basically 5 years of less than 5 years means younger vehicular fleet. However, at the emission standards, because your emissions at the end has to be measured based on the emission norms like BS3, BS4s. So even age-wise, your vehicular fleet is comparatively new, but for the latest emission standards, your vehicles are hardly around 11 to 15%. So even you will say that I have the latest vehicular fleet in my city, but it is not sure that whether your vehicular fleet is polluting at a high rate or they are much more cleaner comparison to the existing. And then using the Webull distribution function, what we are trying to plot here is basically the probability function of the vehicular survive. So at the x-axis, you can see the vehicle life, and at the y-axis, you will have the probability, the survival probability of the vehicle. So as we can expect, if you buy your vehicle in this year, like you will have the 100% chance of your vehicle to flying on the road. But on an average, if you see that 21, like your two-wheelers will have an average life of 21 years. Surprisingly, three-wheelers, which is autos, is having a very big life, that is a 29 years old, which you will not find in a mega cities like Delhi, Bombay, or any other like Chennai. Four-wheeler commercials are basically like Ola and Uber taxis or cabs, and because they uh, don't go, they don't accept the regular maintenance, hence they have a comparatively lesser vehicular life comparison to your private four-wheelers. Now, all these informations will end up in emissions calculations, where we can see that in 2021, we estimated that PM10 will lie around 471 tons per year. Now, interesting thing is that two-wheelers, HCVs, that is heavy commercial vehicles, buses and light commercial vehicles, have some of the same contribution. So you don't, think about it, or you don't pinpoint any particular type or category of vehicle that you have to be reduced so that PM10 will get reduced. Now, the second thing is, or interesting, if you see that in HCV, the major emissions are coming from the BS3. Now, what will happen that if the regulatory agencies follow the convention rule and they will say, okay, remove the older vehicles like BS1 and BS2. But now here, if you see that the major emissions are coming from BS3 vehicular fleet. So even if you will remove the older vehicle, you still have the high pollutant emissions coming from this BS3 vehicular fleet. Now, similarly, because hydrocarbon has the fingers, chemical speciation from the gasoline, so hence two-wheeler has the higher emission loads. And for NOx, which is somehow following the PM10 emissions trend, so hence you have the freight vehicles or heavy vehicles like commercial vehicles and buses, which have the high, emitting around 24 and 25% of emissions coming from the NOx. And similarly for the carbon monoxide, again, because hydrocarbon and CO have the fingerprint from the gasoline sources. So if you want to control HC and CO, you have to target the two-wheelers, not the freight vehicles. After that, because again, like we have done some projections for the 2025 and 30, BAU means business as usual scenario. So there will be no control, emissions, or there's no control measures going to be happened in business as usual scenario. Things will go the way it is going on right now. And for alternative scenarios, for alternative 2021, we have focused on the clean energy fuels like E20, which is a very new thing. Like it just from the last 5 years, it has started in the Indian fleet. And in 2030 R, which is a realistic, what we are saying is basically advancing those cleaner fuels, plus phasing out the high emissions vehicles, which you will find in the major cities, but not in the tier 2 cities. And at the end, you will focus on the city specific emissions by declaring some particular busy stretch as a low emission zone, which is again a very new thing in Indian context. Now, just a visualization, if you see on the left hand side that 2011, the city, the surface area of the city was very less comparison what we have in 2021. City expanded at a very rapid rate. And this particular road is basically a highway, which one direction is going to the Hyderabad and one other to the neighboring city called Guntur. And what will happen in alternative scenario, if we will just, shift the emissions on that particular road from the outer of the city by constructing or by, having some different roads as a highway. So the findings shows us, irrespective of any emissions, scenarios, whether it is business as usual or alternative, emissions going to be reduced, which is a very good thing, because you have now the BS6 or the latest emission standard norms vehicle with you. Hence, the reduction is, or emissions is going to be reduced. But the thing is that if there is no additional control measures, and the vehicle will start increasing, and your reduction measures is going to be balanced by the number of vehicles has been increased. So with the help of alternative scenarios and low emission zones, electric energy consumption, your scenario, the reduction is expected or projected to be reduced by around 50 to 62% for NO2 and PM10. And the major impact will obviously going to happen on the buses and the freight vehicles like heavy commercial vehicles. Now, again, similar, you can see that for PM10 and NOx, freight vehicles and buses were the dominant one. But here you will see all the blue colors, which shows that the two-wheelers are majorly focusing on the carbon monoxide and hydrocarbon. So again, you have to see that how come your cities are, getting disturbed by a particular type of pollutant species, and based on that, you can take some regulation measures. Now, once you have the overall emissions, we are trying to project those emissions on the road basis so that you can, like this map is basically helpful for the regulatory agencies where they can easily see that which particular road has the higher emission load. And the blue square, if you can see, is showcasing the hotspot. So for carbon monoxide at the different scenarios, even if you will able to achieve all this, policies and measures which has been implemented, there is still some junctions or some pocket of the city which still showing the red colors. It means that even like you required very hyper local interventions for those particular areas, so that those areas can also be have some less emissions comparison to the other part of the cities. Okay, so once you have done, the second thing that we have understand here, because of the policies which have been implemented, we can see that the conventional fuel like gasoline and diesel is reducing, like from 2021 up to alternative scenarios 2030 showcasing as a green color. We can reach 46% of reduction comparison to 2030 business as usual scenario. Similarly, for diesel, we can reduce 31%. However, E20 or electricity, which is the new fuel for the vehicles, are going to be increased. And what will happen with that? With the reducing or with the reduction of the conventional fuel, your direct CO2, which is the tail, CO2 coming from the tailpipe or exhaust, it is going to be reduced, which is a very good thing. For our study, we estimate that around 29% of the reduction can be feasible from the 2021 if we will successfully able to implement all the scenarios and the policies. But the indirect CO2 from where it is coming, as of now, for the city and for the state, around 57% of the fuel is still coming from the conventional, or we call the thermal power plant. So even if you will, penetrate electric mobility or electric vehicles in your city, but because your energy demand is coming from the coal-based thermal power plant, you will not able to succeed what we called as in zero emissions. So hence, even if you will able to reduce around 29% of the exhaust emissions, but the balance or the comparatively load of your city is going to be somewhat similar, because the indirect CO2 is going to be increased from 25 gigagram up to 185 gigagram in the coming futures. So again, key finding is that obviously in alternative scenario, we can have a pollutant reductions. Conventional fuel and exhaust CO2 is also going to be decreased. However, the indirect CO2 burden is going to be increased because you still don't, focus on the renewable energy sources, which is very important for the cities as well. What we recommend in our study is that still we don't have Indian specific testing or real driving emissions testing protocol. Hence, for some of the components, we have to still depends upon the European countries and the Western worlds, because emission brings a lot of uncertainty with them as well. So what we required is the in-house, testing or measurement systems, decentralized electric vehicles charging, because still in India, electricity or electric mobility is a very new concept. You don't find many electric vehicular charging stations at your doorstep. You have to travel somewhere and then you have to charge in and all those things. And the future recommendations that, the next phase of our study is that once you know the emissions, how come you relate those emissions with the health benefits with the citizens as well? That is very important. Developing the local based emission factors. As I said, we're still, for some of the data input, we're still relying on the European countries and developed countries. And with the help of the Python and the YOLO deep learning model, we are trying to develop a real-time emission prediction. So with the help of CCTV footage, the real-time footage can be fed into the model, and it will give you the real-time emissions. So these are the two papers through this cities we are able to publish. I shared the link to convener. They can share with you guys. And for the acknowledgement, we have a very good team led by my professor Suresh Jain from Civil and Environment Engineering departments, and the different peoples. The second author of the of our study is right now in NUS doing his PhD. Clean Air Research Group from IIT Tirupati, and the funding agency called University Grant Commission and Andhra Pradesh Pollution Control Board, which help us to perform this study. some references that I have used, and this is the thank you slide. Thank you very much for giving me this opportunity, and I'm happy to take questions. Thank you.
Thank you, Dr. Sharma. Very interesting presentation. We actually have 3 questions now in the chat.
Sure.
So the first is, what are the mandated adoption years for BS 3, 4, and 6?
Adoption year. Okay. So again, this is, I'll just wait, give me a second. Okay. So this is again very important. I'll quickly go to this, my road transport policy slide, because what happened initially in in India, the implementation level is not at the national scale. For example, BS3 has been started somewhere around in 2010 for only 6 mega cities, not for the other cities. Very recently from the BS6, the emissions has been implemented on the national level. But before that, for example, BS4 has been implemented in 2000, around 15 in cities like Delhi, Bangalore, but in 2017 in the other cities. So hence you cannot, implement the same data structure for all of the cities.
Okay.
Yeah.
The second one is, given the prevalence of heavier vehicles, do you know what the contribution of brake and tire is? Is 2 p.m.
So non-exhaust emissions we have measured, but I haven't presented in my this presentations. We were getting around 90% of the non-exhaust emissions. However, I would say in that 90%, what I'm saying is basically majorly coming from the road dust resuspensions, not brake and tire wear. I cannot 100% say that a brake and tire wear has a significant contribution, because we don't have emission factors for brake and tire wear, at least for Indian conditions. But it's a significant amount. Yeah.
Okay. Thank you.
Yeah.
And we have actually 4. Okay. Do you have thoughts on development of alternate modes of transit, especially cycling and local trains within the urban core?
Yeah. So we have metros in our cities, if you know, obviously, because cycling is also a very important transportation, mode, for at least for the small patches you can have. We have implemented sub-suggestions to the Vijayawada city regulatory agencies, and I hope that they will implement very soon. But again, until unless you will not, you have to strong your public transport, structure, so that the reduction can be feasible and you can see the changes for the coming future.
Thank you. Sure. And the last one is, transport is a major source of emissions in Kenya, caused by old fleet mainly. Interesting to learn more about emission inventory and projections. Oh, it was a comment, not a question, sorry.
Okay. No,
yeah, very interesting too.
Thank you very much. And I shared the one of my another paper as well, which we have done. We have used the AI model for measuring the road transport emissions. Maybe you can look up to and implement that in your in your city as well.
Yes. I was actually very curious about your identification AI model.
Okay.
I'm just wondering, what is the accuracy of that camera identification?
Sure.
Have you ever done like a manual count to do a validation? Because I had to do it when I was in Colombia. So I'm just wondering.
Yeah. So, as I mentioned here also, that we are able to achieve 93% accuracy in detecting and counting vehicle. So if you'll see that the guy in the middle is that like me and him both have trained this model. The only problem that we have received is at the night times. So when you have the dark, you don't have sufficient light. At that time, maybe the model is not able to identify the vehicles. But somewhat we are getting 93% accuracy, and we have validated this with the manual counting as well.
Okay, big work.
Yeah, thank you.
Well, thank you, Dr. Sharma. I think we're at the end of the question and answer. Oh no, is there a question, Sachin? Do you have another question?
Yeah,
okay, go ahead.
So yeah, Manoj, it was a very big, very huge work. And with this small team, how you managed to do this? And I don't know how much year it took you to like
Yeah.
start this work and end. But I was curious to know how did you collect this activity data for the transport?
Huh.
Because that's a very big task
Yeah, yeah.
to do that.
So again, we were around 5 to 6 people for to conduct this study, and it took around 1 or 1.5 months just to collect the activity data. First, we tried to contact traffic police to have the CCTV footage, but obviously because of lots of bureaucracy and administrative reasons, they were not agreed to give us. And then we thought, okay, better to jump on the road and have the recording for ourselves as well. So we have recorded at the morning time, at the night time, in the afternoon time, in the late night hours as well. And to collect the fuel vehicular characteristics, as you can see at the different fuel stations, we ask different questions from the people about their vehicles performance, their fuel mileage, their vehicle efficiency, all this type of questions that we have asked. 1 to 2 months it took us to collect the data, and then it's just about the modeling and do the calculations.
Great. And I have a follow-up question as well. If we look at the efficiency of the engines of three-wheelers and
Yeah,
four-wheelers as
yeah,
compared to the two-wheelers, so
yeah.
it's a normal thing that NOx emissions are normally higher than in two-wheelers as compared to the three-wheelers and four-wheelers. But your results, if you look at the projections,
Yes, yes,
they are like almost similar. So what
yes,
do you have
yes,
any comment on that? Like how
yes,
is that
yes.
possible?
So I'll say that NOx is majorly, I'm pretty sure you also know about that, it's a fingerprint of the diesel emissions from the diesel combustion. So for these, see again, these are the tier 2 cities, and you will find huge number of two-wheelers comparison to the other type of vehicles. So because of the high, number of the vehicle itself, somehow it's balancing the other vehicle contribution, especially in case of like Vijayawada.
Okay.
This results definitely not be the same for cities like Mumbai or New Delhi, but for the tier 2 city, you can expect these type of findings.
Yeah, and the last question that I have is like
Yes,
with the coming in the new biofuel that we are using, it's
yes,
blended, it's
yes,
all blended fuel.
yes,
So how those are going to like that's a buzz question nowadays
yes,
among the
yes, yes,
scientists
yes.
that are working. How those emissions are going to like whether the emissions are going to reduce or they are going to like increase
Uh,
often.
I don't want to comment directly here because what happening that this ethanol blend fuel is implemented on the city without any in-house study has been performed for Indian cities. What we are seeing is that some studies has been done in the Europe or in the China where they are claiming that uh, pollution can be reduced using the ethanol blend fuel, but the contribution I am not sure how much is the how much is the contribution. But I think 1 or 2 species they are saying, I think carbon monoxide they are saying that it is going to be reduced.
Okay.
But being as a warning, it will definitely impact your fuel efficiency.
Yeah,
Yeah.
that's obvious.
Yes.
Yeah, thank you, Manoj. It
Sure.
was a very big task. Like,
Sure. I'll stop my screen from here. Is it?
yeah, sure.
Yeah. Sure.
Well, I think we're at the end of our ECR seminar for today. Thank you very much for everyone who joined. You can email Dr. Dutta, Dr. Sharma, if you have any further questions. But yeah, thank you so much for today's speakers and the attendance. All the questions were really good, so thank you very much. And I hope to see everyone in the next seminar. Yeah, thank you. Thank you very much. Have a great day, everyone.
Thank you. Thank you for
Thank you
organizing.
very
Thank you,
much.
everyone. Bye
Bye
bye.
bye. Take care, everyone.
Bye.
Bye.